Welcome to our second unit in Module 2, the History of Science. And in this one, we're going to look at a particular example and go through it in a little bit more detail. And that's the history of models of the solar system. And this one actually links directly in with your second portfolio item, which we will look through at the end of the module, so after Unit 3. So it's important to pay attention to this one. And for many of you, some of this will probably be quite unfamiliar. You'll know basic ideas about the fact that the sun is the centre of our universe and we revolve around the sun, but you may be very interested to know how we've gotten to that view based on earlier views. So we're going to begin our journey by looking at an ICT. Now this ICT is around about 5 minutes in length and it is quite comprehensive, and we're going to unpack some of the ideas that are contained in it in the slides after the ICT. So let's have a look at this first.
Galileo was born into a world where each morning reaffirmed the common view that the sun moved around the earth. This belief was confirmed as the sun appeared to pass overhead each day. From ancient times, astronomers had tried to account for the observed motions of heavenly bodies by assuming that they were attached to transparent crystal spheres, rotating sphere within sphere. The Greek astronomer Ptolemy worked out the system in great detail to explain the motions of the sun, the moon, the stars, and the planets, all that could be seen with the naked eye. At the center of Ptolemy's intricate system sat the Earth, solid and unmoving.
The Ptolemaic system was filled with ingenious geometrical devices. It made it possible for people to compute where the planets were to be, and this was useful, let us say, for astrology. It was useful if you just wanted to keep track of where things were in the sky. But it wasn't perfect.
60 years before the telescope, a Polish clergyman, Nicholas Copernicus, noticed that the calculations needed to predict the positions of the planets in the sky would be simplified if he assumed that the sun, rather than the earth, were at the center of the universe.
For decades after his book, most astronomers simply suspended judgment. The reason was that there was no observational evidence that the earth moved. In fact, it seemed almost silly that the earth moved.
In the Copernican system, the Earth was never still. It had two separate motions, revolving around the sun each year and spinning on its axis once each day.
The thing that Copernicus suggested just made him really the laughing stock of Europe, because he was saying here is the Earth is actually whizzing round at a huge speed, about 700 or 800 miles an hour. That's just going round on its axis. And in addition, it's going round the sun at about 30 miles a second. I mean, they were saying, this is just absolutely ridiculous. I mean, look at the ground. It's as solid as you can see. Clearly, the Earth is not moving. Nothing could be more obvious than the fact that the Earth isn't moving. If it was moving, everything would be flying off it. I mean, church steeples would fall down, birds couldn't keep up with it, clouds would go disappearing over the western horizon and things like this.
Galileo had read Copernicus and already suspected that the Copernican system was correct. But even with his telescope, he did not see a way of proving that the Earth moved around the sun.
For him, demonstration was the mark of science. For something to count as a scientific claim, it had to be demonstrated. It had to be conclusively shown to be the case. Anything short of that was called conjecture or opinion.
While he searched for a demonstration, a letter arrived from one of his followers, Benedetto Castelli, suggesting that the planet Venus could hold the key.
My dear Galileo, if Copernicus is correct, and Venus revolves around the sun rather than the Earth, it is clear that she would be seen not unlike the phases of the moon, sometimes as crescent and sometimes not. Pray tell me if, with your wonderful telescopes, you have noticed such an appearance?
To the naked eye, Venus was just a point of light, but through his telescope, Galileo saw the planet as a disk. Over a period of months, Venus changed from a small disk to a larger crescent. Galileo immediately grasped that in a sun-centered system, this crescent would appear as Venus circled in an orbit between the Sun and the Earth. Venus must be revolving around the Sun rather than the Earth. Years later, Galileo finished his great book. It was called Dialogue on the Two Chief Systems of the World.
It is a debate about the world systems. Is the sun the center of the universe? Or is the earth the center of the universe?
I always think that his dialogue on the two great world systems was the persuasive book that made it intellectually respectable to believe in a moving world, a sun-centered universe. It was the book that won the war.
Well, I hope you found that quite fascinating. I really enjoy watching that clip because it really shows the impact of scientific thinking. So what we're going to do is we're just going to review some of those early ideas and you know, basically where we've come from to where we are now. So basically our first scientists had that view that everything in the physical world was part of a well-ordered system. So our first scientists really tried to create representations of the universe which would help them explain how it worked. So remember, these early scientists had no telescopes, you know, they had no technology. So they just had to rely on what they could observe. And basically that was the sun rising and setting, that was looking out at the stars, trying to look at observable phenomena in the universe, which is really quite limited. So even back to Aristotle, which is 384 to 322 BC, the universe consisted of a terrestrial region, which is like an Earth-centered region, and a celestial region, which was everything that was outside of the Earth. So that included within our atmosphere and then also outside of our own atmosphere into the universe. And within his model, he proposed that the terrestrial region was subject to change, but the celestial region was unchanging. So this idea of a fixed universe. So the division's convenient because it allowed Aristotle to provide different types of explanation for the movement of objects in the different regions. So in the celestial region, the moon, sun, planets and stars were all attached to solid transparent spheres which moved in perfect circles around the Earth. Now again, it seems quite bizarre to us now knowing what we know, but back then you have to put your mind back to what evidence was available for these people to make their conjecture. So here's a graphic. So here's our Earth here. So in this model, there was an air region, which is clearly our atmosphere, this fire region. Here's the moon. Here's the observable planets. So Mercury and Venus here. Here's the sun, which was considered to be in this position. And the other planets, Mars, Jupiter, Saturn. And then the rest of the stars were in this outermost sphere. So everything in the terrestrial region was made from a combination of 4 elements. And so this is our early chemistry. So earth, water, air and fire. And each element had its natural place in the cosmos and always strove to return to it. So back before we had ideas about gravity, a rock when released would fall to the ground because it was made of earth and it just wanted to return to its natural place. So that was the explanation. So we didn't have the explanation of masses attracting other masses back then. That wasn't developed. This geocentric or Earth-centered model of the universe was accepted for over 2,000 years. So our modern view of astronomy, in which the Earth rotates on its axis and revolves around the sun, evolved during a time called the Scientific Revolution. So you can see from these dates, 16th and 17th century, which is basically the 1500s and the 1600s. So really only 500 years ago, which in the scale of the Earth's history, it's not that long ago. And I'm not sure how your history is, but we had the Renaissance period. So the scientific revolution occurred after the Renaissance. And this period in time provides a transition between what we call the medieval and the modern world. So around the mid-1500s, there were 2 models that existed. We had our geocentric, Earth-centered view, which was the dominant view, and then a heliocentric, helio meaning sun. centered model. Now, this was if we're talking about paradigms, this was the scientific paradigm that was the dominant one. And the heliocentric was a paradigm that was building up on the side as more and more evidence became available. So here's our geocentric. So you saw in the ICT, Ptolemy was a major figure, associated with this model. So Aristotle first proposed it many, many, many years ago, but the geocentric model was further developed by Ptolemy, and this was around 100 to 200 years after the death of Christ. He was a Greek philosopher, and our early scientists were referred to as philosophers because the scientific revolution hadn't happened yet. He stated that the Earth is a motionless body at the centre of the universe. Celestial bodies move in perfect circles at uniform speeds. The stars were set in a rotating sphere that turned east to west once a day. And the planets, the moon and the sun were also set in separate spheres that moved slower. So it was a refinement on Aristotle's earlier model. And we sort of use this analogy of a rotating merry-go-round. So here's the Earth in the centre. The moon's going this way at a particular speed. The sun's going this way at a particular speed. The stars are going this way at a particular speed. All right, so this was the model he developed. But as observations became more and more detailed, the model became more and more complex. There were more spheres. It became a very convoluted, difficult model. So this is what we're talking about with models. We're talking about it with the atomic model. We use a model to try and help us explain a phenomena. But what happened was the observational quality was fairly poor. And although the model worked pretty well, with more precise observations it didn't hold up. We found issues with it that weren't actually aligned with the proposed model. Many corrections had to be added, and it did not explain some things, such as the changes of brightness of planets. Now, there's a particular phenomenon in science called Occam's razor. And what that means is that among competing hypotheses or theories or ideas, the idea with the fewest assumptions should be selected. So what that means is that if we have a choice of a complex model that may have some limitations or a simpler model that tends to represent the phenomena in general better, we'll take the simpler option. So we tended to find, well, this model's not sufficient. It's not really helping us explain what's going on. So let's move now to an alternative model, which is the heliocentric model. And Nicholas Copernicus was the major proponent that was associated with this model. So around about 1500, you can see he was a Polish cleric, so he was a religious man. Because back in those days, remember, this was just before the revolution, the scientific revolution. Copernicus was dissatisfied with the complexity of the geocentric model. He stated an alternative view, and that was that the motion of the objects in the sky could be explained by imagining, and again, here's that creativity, because they didn't know, they had no evidence, observable evidence for this model. The Earth revolved around the sun once a year, and that the Earth also rotated on its axis. So this was a completely counter view. Could you just imagine? The Earth's the center and everything revolves around it, and then someone comes in and says, no, actually, I think it's the sun that's the center and we revolve around the sun, without a bunch of evidence to support him. So, as you can imagine, the explanation was rejected by nearly everyone at the time. And it also required an acceptance of the idea of an unbelievably large universe. And really, in those times, this idea that man was the center of the universe, the religious worldview, it ran counter to that. So the philosophical and religious belief that man and the earth was at the center of the universe, and man was believed to be superior, not just a part of nature, which is what this view required, but the center of nature. And also this theory ran against the theories of the political powerful churchmen of the time, who really, were basically the leaders in society. So here's one of Copernicus's early drawings, Sol here, which represents the sun. Here's our two planets, here's the Earth. So really, it was quite a refined diagram for someone who really had very little to work on other than his, evolving ideas. You may have heard of these scientists, Galileo and Bruno. They accepted the Copernican theory, but as a result suffered much personal injury at the hands of the powerful churchmen. So Bruno dared to suggest that space was boundless and that the sun with its planets was just one of many similar systems. So he even put forward a more radical idea that there's not just one solar system, there's countless solar systems. He even suggested that there might be other intelligent beings equal or possibly superior to ourselves. So can you just imagine how well that would have gone down? So that was considered very blasphemous. That ran in the face of a religious worldview. And he was basically burnt at the stake for his views. So that was charming. In 1633, Galileo was forced to give a public denial of Copernican theories under the threat of torture and death, and was sentenced to imprisonment for the rest of his life. So we know Galileo, he was the inventor of the telescope, and basically he endured much hardship because of his views, but still held fast to his idea of the scientific worldview. What this shows us, though, is that revolutions in scientific thought, or paradigm shifts, and that's why I wanted to tell you about paradigms, they don't come easily. It's important to note that scientific knowledge is subject to modification as new information challenges prevailing theories. So really, I mean, what this story illustrates most probably clearly is that scientists were people, and they are people, who have to actually have to fight against a system that didn't support them. So I think it really shows our students that human element, in that science just isn't out there and we just discovered it. We actually had to fight for many of these ideas. So there's some basics of our heliocentric model, which is now our scientifically accepted model. And now we know with advances in technology, we can have satellites and various types of astronomical developments, which we can actually now say, well, there we are, there's the Earth, there's the Sun, there are the planets. So the Sun is the center of the universe, it is motionless, and the stars are motionless around the edge. The planets all revolve around the Sun, and the Moon revolves around the Earth. We know the Earth rotates on its axis, giving us our day and night. And the Earth also revolves around the Sun. That takes 365 days, and we get our different seasons. Copernicus also determined the relative distances of the planets from the Sun. And Galileo, poor old Galileo, who was imprisoned, he used the newly invented telescope to provide scientific evidence to support the heliocentric view of the universe. And the way he did that was he actually discovered that Venus actually goes through phases. So if you think about our moon, we see different phases of the moon. Venus basically must orbit the Sun if it goes through phases. So this is due to the fact that Venus can never be more than half illuminated, and Galileo saw all the phases of Venus from a thin crescent to a full sphere with his telescope, which gave us the evidence to know that Venus was also revolving around the Sun, because we could see the different amounts of the lit surface. All right, so Venus can only go through phases if it orbits the Sun. It's a bit like our moon. If our moon didn't orbit around us, we wouldn't see the phases. That's probably less important to you, but it did provide that sort of empirical evidence. So there's lots of new ideas in this unit. I hope you found it a useful example from the history of science. Our second portfolio item is going to focus on lots of the ideas that we've just been through. We're going to go through this at the end of the module, which is after Unit 3. But importantly, just what you may want to do in the meantime is you will need to access the Australian Curriculum Science F to 10 document and be able to locate the Year 7 section to complete that item. So I've put in a link here that should take you directly to the Australian Curriculum webpage, and you can scroll down and get to Year 7. So just make sure you can find that and maybe bookmark it for when we talk about our second portfolio item.